Put the cup to the left of the plate. Put the knife to the right of the plate.
Though voice-controlled robots exist for a long time, most are limited to prepared commands like move up or walk, leaking the ability to interpret commands, which deviate from prepared sentences. Language transformers have proven successful in interpreting text and extract a meaning out of it. Besides the classical application of language translation, recently transformer encoders were also employed for text creation, most notably GPT-3 by OpenAI, or image generation, for example the clip transformer, used by DALL-E from OpenAI. Here, we want to use transformers to map text and voice input to robotic movement. We want the robot to execute a simple command. Move the object A to a position relative to object B. This position is defined by a preposition C, left or right. The objects are referred to via indices. Therefore, we have a three-dimensional vector, which we call the command vector. The transformer aims to map a sentence, for example, place the knife to the left of the cup, to such a three-dimensional command vector. We employed a transformer encoder and attached an additional linear neural network layer to map the word encodings to a single sentence encoding vector. The command vector is just mapped onto itself via an identity transformation, which constitutes a simplification of the joint transformer encoder model. In order to execute the command, we use reinforcement learning, specifically Deep Deterministic Policy Gradient (DDPG) based hindsight experience replay (HER), in order to train a robotic arm to pick and place an object. This we will refer reinforcement learning model to as the robotic model. DDPG is an adapted version of deep Q-learning, where a neural network maps the observations to an action vector in a continuous action space. This network is called the policy network. In addition, a second network, called the Q network, will learn to approximate the Q value for a state action pair SA. Both networks are trained simultaneously until the policy network successfully maximizes the real reward in the system. HER is an additional improvement to this model, where the model trains with artificial goals in order to learn faster in a system with sparse rewards. The robotic model as well as the transformer are trained separately. We then combined the two models, where the voice is recorded by a microphone, converted into text by the Python package speech recognition, translated to a command vector via our trained transformer and then executed via our trained robot arm. The result is demonstrated in the following.
Move the cup to the right of the plate. Put the cup to the left of the plate. Put the knife to the right of the plate.
Possible improvements remain. Currently, the robot arm can just move through an object, which is not physical. In the future, the robot could be trained to move around an object in order to reach a goal. Moreover, using 20 CPU kernels instead of 8 would enable to perform the more complex task of grasping the object with a hand, instead of just picking it with a knob end. I am currently working to make this also possible on my 8-kernel machine and hopefully present this in the future. Third, the microphone has poor quality, which sometimes leads to mistakes in the voice-to-text mapping, for example white instead of right. Fourth, I would like to connect this robotic arm with an armature body to let the armature walk around in a setup to pick and place objects in different rooms in a 3D model of an apartment. Finally, building a real robotic arm will be the final goal, to move the model from a 3-dimensional simulation to a real-world setup. For this I bring experience with SolidWorks, 3D printing and electronics based on the Arduino microcontroller as well as mechatronics, using Python on a computer to control mechanical movement of linear actuators.